Welcome to The Explainer. Today, we're diving into a genuinely fascinating architectural concept, rebuilding the time machine for modern data systems. We're talking about a dual-purpose data versioning system built specifically for modern backends and AI engines. So, if you've ever banged your head against the wall trying to manage historical data without completely tanking your primary database's performance, well, you're absolutely in the right place. I want you to picture something for a second. What if your database could literally time travel? Like, what if you could just hit a button and instantly pull up the exact state of your entire system from precisely last Tuesday at 3 p.m.? Usually, in conventional setups, a user updates their profile, a transaction fires off an update statement, and bam, it just overwrites the old bytes right there on the disk. We call these destructive writes. And as we're going to see, they are causing some massive headaches for modern engineering teams. Okay, let's dive into this. Here's our roadmap for today. First, we'll look at the problem with erasing history. Then, two systems with opposing needs. After that, we hit Phase 1, operational time travel, followed closely by Phase 2, analytical data flows. And finally, we'll wrap up by evaluating the trade-offs of this entire architecture. Section 1. The problem with erasing history. Why standard destructive writes fail modern systems. Traditionally, we've treated databases strictly as state machines, but relying on that old destructive write model, it really falls short today. Why is that? Well, in modern architecture, data history is an absolutely incredible asset. When your system relies on just overwriting old data to save a bit of space or, just to keep things simple, you completely lose the ability to audit those changes. Think about it. If you can't recreate that exact system state from last Tuesday, you can't reliably debug a complex distributed system. And you definitely can't retrain an AI model on a deterministic feature set. To really drive this point home, check out this quote from the architecture blueprint we're reviewing. "The past is erased and only the present survives." I mean, it sounds exactly like a line from a dystopian sci-fi movie, right? But it is literally what standard databases are doing every single millisecond. They are actively destroying highly valuable historical assets that could otherwise be used to make your software infinitely smarter. Moving right along to Section 2, two systems, opposing needs, the operational versus analytical dichotomy. So, we basically have a fierce battle happening here between two totally opposing database requirements. On the left side, we've got the backend platform, your standard OLTP. This side absolutely requires a clean third normal form relational database. It demands low-latency index lookups, transactional ACID safety, and the ability to toggle specific entities back and forth in time. But now, look over on the right at the AI layer, your OLAP. AI models, they don't care at all about individual point lookups. They need massive, immutable batch datasets. They want chronological flat streams, like Parquet files, and they absolutely demand 100% training reproducibility. Honestly, these two systems are like characters in a movie who just absolutely hate each other. If you try to force both of these needs into a single custom mirror table, you're going to break your 3NF constraints, ruin your migrations, and just create severe system bottlenecks. So how do we actually fix this? The source points us to Command Query Responsibility Segregation, or CQRS for short. By definition, this is an architectural pattern that completely separates the data structures used for reading information from the ones used for writing it. And this brilliantly illustrates how we can finally stop forcing one single database to do two entirely opposing jobs. CQRS steps in as the ultimate peacemaker for our dichotomy, allowing us to build a true dual-purpose architecture. All right, Section 3, Phase 1, Operational Time Travel. High-speed time travel in 3NF. How do we actually build this high-speed time travel right into our backends? Well, the secret sauce here is totally abandoning those clunky application-level mirror tables. Instead, we implement bi-temporal validity periods natively within the relational engine itself. Think Postgres. Every version table gets an immutable timeline partition using two very specific timestamp boundaries, valid from and valid to. So rather than just slapping a created or deleted date onto a row, we're creating a strictly defined active period for every single version of a record, right there inside our 3NF database. And that leads us to the immutable mutate pattern. When you look at the logic sequence here, the absolute golden rule is this: the application layer never executes a standard destructive update, like ever. Instead, it wraps two actions inside a single, incredibly safe database transaction. Step 1, you close out the current active version by setting its valid to column to the current timestamp. Then, step 2, you insert a brand new row containing the modified data. You set its valid from to the current timestamp, and you push its valid to way out into the future, like December 31st, 9999. It's a beautiful pattern because it elegantly preserves your 3NF relational integrity without the application ever actually performing a destructive write. But honestly, the best part, this setup allows for seamless time jumping. Since the database engine keeps all the versions inside a unified structure managed by these time bounds, switching states back and forth is computationally really cheap. You don't need any complex SQL union operations across a bunch of scattered mirror tables anymore. To grab the current state, your application simply filters for where now falls between valid from and valid to. And if you want to jump backward in time, you just filter by specific past timestamp between those exact same two bounds. It is incredibly clean and so efficient for the application layer. Let's move to Section 4 and see how this builds. Phase 2, Analytical Data Flows, Linearized Data Streams for AI Engines. Now, as great as that backend solution is, if you try running massive AI aggregation queries across millions of historical rows, you're going to immediately saturate your operational database's I/O. To bridge that gap, we use an asynchronous pipeline. It all starts with the operational DB we just configured. From there, change data capture tools, something like Debezium, for example, stream every single incremental version insert straight out of the OLTP database logs. Those streams are then pumped asynchronously right into a high-performance columnar data lakehouse like ClickHouse or Apache Iceberg, which is just perfectly optimized for our machine learning feature stores. And this matters immensely for AI practitioners. By transforming those rows into columnar timelines, these analytical lakehouses allow for native AI time travel. Data scientists can query exact snapshots of the data using Git-like semantics. I mean, literally, using SQL commands like for system_time as of a very specific date. This guarantees a perfectly reproducible feature matrix with absolutely zero data drift over time. You can even layer this whole thing with tools like DVC or LakeFS to branch, commit, and lock data versions right alongside your actual model code repository. It's fantastic. Section 5, Trade-offs of the architecture. Evaluating the engineering costs. Look, no system architecture comes for free, right? Running a time machine definitely has its costs. But what's really interesting about this slide is the clear contrast in the trade-offs. Take the storage footprint, for instance. That's a high overhead. Keeping every single version scales your storage linearly, so you absolutely must have explicit cold storage retention policies in place. Backend code complexity, that's about medium. It's mostly abstracted by ORMs these days, but you do still have to bind timestamps on your reads. Relational integrity requires a pretty high shift in how you think, moving over to composite primary keys and swapping out cascading deletes for logical soft deletes. But check out that bottom row, AI feature readiness. The friction here is incredibly low. You get zero performance degradation on your production user environments during massive model training runs. And honestly, for modern data-driven companies, that benefit drastically outshines the extra storage overhead. So, the crucial takeaway here is simply this. Separating responsibilities really works. CQRS successfully tackles that dichotomy we talked about. By using Bi-Temporal validity inside your 3NF database, you preserve those high-speed lookups for your user applications. And by streaming via CDC into a columnar lakehouse, you guarantee deterministic, historical flows for your AI pipelines. You manage to satisfy both systems without breaking the overarching architecture. Data versioning isn't just some boring internal audit checklist anymore. It is truly becoming a foundational pillar of building intelligent software systems. I want to leave you with a final thought to chew on. Take a hard look at your own architecture. Is your current backend truly ready for the AI era? Or is it still out there quietly erasing history every single time a user updates their profile? Because if it is, it might just be time to start rebuilding your very own time machine. Thank you so much for joining me in this explainer. I highly encourage you to look a bit deeper into bi-temporal data modeling to see how it could transform your own systems. Keep learning, and I'll see you in the next one.